Welcome to Meat Boy Physics 101. Today we're going to cover how Meat Boy's horizontal and vertical movement is affected by walking, sprinting, gravity, ground jumps, and wall jumps. To do this, I'm going to use libtask to collect experimental data one frame at a time, and then we'll analyze it to find out what's really going on, or at least a good approximation of it. This means that all observations will be based off the Linux version of the game. However, everything in this video should also be true for the OG version Steam Beta on PC. First of all, there are two important things to know about Super Meat Boy physics. Number 1. The movement that happens during a frame depends on the length of that frame. For example, running the game at 30 FPS means that everything will basically move twice as far per frame as when running the game at 60 FPS, which makes up for the fact that there are only half as many frames. Number 2. When running the game at 60 FPS, which is required for almost all speedrun categories, the frames do not each take a 60th of a second as you might expect. Rather, the first frame the game is open takes 16 milliseconds, the second and third take 17 milliseconds, and then the 16, 17, 17 pattern continues until you close the game. This means that even if you perform the exact same inputs starting from the exact same position with the exact same speed, you could potentially end up in one of three places, depending on where in this 3-frame cycle you started. In practice, this is not usually noticeable in real time, although there are situations where it matters, in which case certain things can have effectively a random 1/3 or 2/3 chance of working. A good example of this is Nijeclipse, which I'm not going to talk about here, but I'll link a tutorial in the description. Anyway, although it's a slight difference, it's pretty easy to detect with the use of save states and frame advance. Yep, that's me. You're probably wondering how I got into this situation. Well, it all started about a second ago when I jumped off the top of the level. Now I'm going to see where I end up if I unpause on this frame versus 1 frame later versus 2 frames later. We should expect to see Meat Boy move slightly less far if we unpause on a frame that has a remainder of 1 when divided by 3. In this case, the last one. Watch Meat Boy carefully and you should be able to see this. With precise pauses, you could skip any 16 millisecond frame that you wanted to, but the time lost for pausing would outweigh the benefits of the longer frame, unless there was a particular skip that required it. You can see one such skip in 720X in the 106 tasks, which again I'll link in the description. I'm not going to worry about manipulating the frame lengths with pausing in this video, but it's just important to keep in mind as we're collecting data that they may complicate things. Let's talk about gravity. In real life, assuming negligible air resistance near the surface of the Earth, an object in freefall will accelerate downwards with a constant acceleration of roughly 9.8 meters per second per second. Let's assume that this more or less applies to Meat Boy as well, and that each frame, Meat Boy's vertical velocity decreases by some constant g times the frame length, and then his vertical position moves by his vertical velocity times the frame length. Now I'm going to see how many frames it takes Meat Boy to fall 1 block, 2 blocks, 3 blocks, etc., and hopefully this assumption is correct, and we'll be able to find a value of g that fits all the data. For consistency, we'll have the first frame of downward movement be divisible by 3 in all these examples. Alright, here we've got a plot of this data. The x-axis is number of frames, and the y-axis is number of blocks fallen. So, we have this mystery acceleration constant g, and if we just forget about the different frame lengths for a second, assume everything is a 60th of a second for simplicity, then on the first frame, each frame the velocity will increase by g over 60, and then the position will be updated by whatever the velocity is, divided by 60. And so the position after n frames would be g over 60 times 60 plus 2 times g over 60 times 60, all the way up to n times g over 60 times 60. So we can factor out this g over 60 times 60, and then we're just multiplying by the positive integers up to n, which there's a formula for that. So now let's add, one last thing. Instead of n, we're going to use the floor function, just so that we're only computing this at like a whole number frame. Now let's add a slider for G, test things out, and it looks like 10 is way too low, so let me set the upper bound to like 30, 20 to 30, and okay, we're almost there. So it seems like somewhere around 27, 27 and a half. If we zoom in a little bit, we can see this is still too low. We want these points to be sort of sandwiched in between the lines because we want the frame before it to not have reached the point, and we want the frame after it to have reached the point. So this is a little too low. If we go up to like 27.8, we can see that's a little too high now. So somewhere in the middle, we'll call it 27.5 because that's a nice round number, and then we'll see where that takes us. Next step is to do the same thing with walking and sprinting, but there are a couple things about horizontal movement that I want to mention first. For one thing, I'm going to assume that whether you're in the air or on the ground doesn't affect your horizontal movement at all, which as far as I know is true as long as you keep going in one direction. Also, it's pretty clear just from playing the game that you don't accelerate horizontally forever. There's some maximum speed, and it's faster when you're sprinting than when you're not. So in addition to looking for walking acceleration and sprinting acceleration, we'll also be looking for walking max speed and sprinting max speed. Finally, since all this horizontal testing is going to be based on lining up with one wall and then walking or sprinting until we hit another one, it's important to note that you can actually be on a wall without quite touching it. If you've ever seen Meat Boy slide straight up a wall, this is why. There's a very small window where you're allowed to wall jump, but you haven't actually hit the wall, so you still have your horizontal speed. Then when the wall jump adds to your horizontal speed, all it does is cancel your current speed, instead of making you move in the opposite direction. Anyway, I can't think of a good way to derive this window experimentally, so I'm just going to take it as given that it's a 20th of a block. This value was found a long time ago from digging around in the code, and actually all the horizontal values I'm going to derive have also already been found in that way, but I've never seen the vertical stuff posted anywhere personally. Anyway, here's some more experiments.